Welcome to this explainer on the Azul GUI framework. If you're a new maintainer, or maybe just curious about what makes a modern UI engine tick, you've come to the right place. We're going to map out the entire architecture for you. So here's the game plan. We're going to trace the full journey from a single line of your code all the way to the final pixels on the screen. We'll kick things off with how a window even gets created, then dive into how the layout is planned out, how assets like fonts get prepped, how it all gets rendered, and finally, how the whole project gets documented and shipped. Okay, let's get right into it. At the most fundamental level, before you can draw a single button or display any text, you need a window, a place on the user's desktop to actually draw on. This is our canvas. I know, it sounds pretty obvious, but this is the absolute foundation. Everything that Azul does, every layout calculation, every animation, every single user interaction, it all happens within the boundaries of a window. Think of it as the root of the entire visual tree. So, how does Azul manage to work on Windows, macOS, and Linux without being a huge mess of platform-specific code? Well, the secret sauce is its DLL crate. Now, in the Rust world, a crate is just a package or a library. This particular one is a brilliant bit of abstraction. It gives you one clean, consistent API for creating windows and handling events, mouse clicks, key presses, no matter what OS you're on. All right, we have our canvas. Now we need a blueprint for what to draw on it. This is the layout phase. It's where Azul takes your high-level styling rules and turns them into a concrete plan of exactly what goes where. The layout engine is a really methodical, step-by-step process. First, it parses and figures out all the CSS rules. Then it calculates the size and position of every element using what's called the box model. After that, it builds formatting contexts to handle different layout types. And finally, it spits out a master plan called the display list. Just like on the web, everything in Azul's layout is basically a box. The engine uses a struct called boxprops to work out the final dimensions of each element. Now, if you're a maintainer, this is huge. That struct is where the core layout logic lives. So if you're ever debugging why an element is the wrong size or in the wrong place, this is your starting point. Now, this is really interesting. Check out how Azul thinks about documents with pages, like a PDF. Instead of treating each page as its own thing, the engine imagines one single, infinitely long vertical canvas and lays everything out there. The page breaks are just calculated as empty dead zones in between. It's a really clever way to solve a complex problem. You ever wonder how UI knows which element to draw on top of another one? The answer is stacking contexts. Certain CSS properties create a new stacking context, which is basically a new layering group. Elements inside that group then get painted from back to front based on their z-index. This is what lets you build complex overlapping interfaces. And this right here just shows the incredible attention to detail. To render a simple table correctly, Azul follows the official CSS spec, which says you have to follow a strict 6-layer painting order. It does the main background first, then columns, then rows, and finally the cells on top. This isn't just close enough, it's about perfect compliance. So after all those calculations, the box models, the stacking contexts, the paint orders, the layout engine's job is done, and its final output is this one critical data structure, the display list. Just think of it as a simple ordered to-do list for the renderer. Draw a blue rectangle here, draw this text there, apply this effect here. So we've got our blueprint, the display list, but it's still just a bunch of abstract instructions. To really bring it to life, we need to hook it up with the actual visual content, and that's where things like fonts and images come into play. I mean, modern UIs aren't just solid colored boxes, right? They are rich with typography, vector graphics, and images. So how does Azul take all these external resources and get them ready for the rendering pipeline? Well, the framework has specialized loaders for each type of asset. It knows how to find and load fonts from your system, how to decode images, and how to parse structured data like XML and SVG. And what's really crucial here is that it caches all of this data aggressively, so it doesn't have to keep going back to the disk. That is essential for a smooth, high-performance UI. All right, we have our blueprint, the display list, and we have all our assets ready to go. It's finally time to put some paint on the canvas. This is where the renderer takes over. Now, Azul doesn't try to reinvent the wheel when it comes to rendering. Instead, it delegates all the heavy lifting to WebRender. And yep, that's the same high-performance engine that Mozilla developed for Firefox. Because WebRender is also written in Rust, it integrates perfectly, giving Azul an incredibly fast and battle-tested way to draw complex UIs. To make sure an app can run pretty much anywhere, Azul actually gives you two rendering paths. The default path uses WebRender on the GPU for the best possible performance. But if you're on a system that doesn't have good graphics support, it can fall back to a software renderer that just uses the CPU. Sure, it's slower, but it guarantees your app will still run. So, what's WebRender's secret to being so fast? It's all about avoiding unnecessary work. As a maintainer, you'll come across concepts like tile cache, picture cache, and render task in the code. Just know that these are all clever tools to minimize redraws and cache complex operations. Understanding that is key to debugging rendering and squeezing out performance. So the UI is rendered, but our journey isn't quite over. A framework is more than just its runtime code. It's also about how people can work with it, document it, and ship it. So let's look at the toolkit that makes Azul feel like such a mature project. For maintainers, Azul's build tool is an absolute game changer. It automates so much of the tedious work, like updating documentation, checking for API changes, running visual tests, which means you can focus on writing code. It's a huge part of what makes Azul so stable and a great project to contribute to. At the very heart of this tooling is one single file, api.json. This thing is the absolute source of truth for the entire framework's public API. If it ever gets out of sync with the code, the documentation will be wrong, versioning will break, and, well, users will have a very bad day. That's why the build tool is so strict about validating this file. And this is a message every maintainer absolutely loves to see. The tooling is so smart that it can analyze changes in the Rust code and compare them against that api.json file. If it finds a mismatch, it can even generate the patch files needed to get everything back in sync. It's your safety net against accidentally making breaking changes. And that completes the entire cycle. We've gone from the very first step of opening a window to defining a layout blueprint, rendering it with a high-performance engine, and finally packaging it all up into a well-documented, stable release. This whole pipeline is what makes Azul so robust. So there you have it, the map of the Azul engine from start to finish. We hope this overview gives you the context and the confidence you need to dive into the codebase and start contributing. Now there's just one question left. What part are you going to explore first?